Hi there, this is the second lesson, main lesson of the week, lesson 9. The earlier lessons were 8 and 8a for the first lesson of the week. We're still doing forces on charged particles. The last lesson we had a look at electric fields. This lesson we're going to have a look at magnetic fields. If you're keeping up with these learning outcomes in the boat book, this is learning outcomes 9G and 9H. Okay, so just to go over not very much really about electric fields. The idea of electric fields is that they accelerate particles. So that means that they can start off very slowly, excuse me, and they get accelerated, so they're going faster and faster. And if you continually put some particles, charged particles, through electric fields, then they can reach very, very high speeds. And the idea of the Large Hadron Collider in Geneva, which we'll be doing more about later in another lesson, is that these speeds can get up to almost the speed of light, like 99% of the speed of light. So the idea of the accelerator is you have a big ring. This is looking down from above, and this ring is many, many kilometers long, and it's a tube. And the particles travel round and round and round through the tubes. They start off actually not moving at all, and they get introduced into the main ring, having been set up in a little, probably in a smaller ring. The smaller ring might be just about the size of a tabletop. And then it goes into a secondary ring, which might be about the size of a big laboratory. And then they get injected into this very, very large ring, which goes on for kilometers and kilometers. Now you can see that this is a circular path. So although the electric field will accelerate particles, all they'll do is accelerate in a straight line. So what we need is some way of getting the particles to go round in a curved path. And that's what the magnetic fields do. The magnetic fields they bend or deflect particles. So what you've got in your accelerator, if it's like the Large Hadron Collider, is you've got a combination of electric fields and magnetic fields both working together, one to get the particles up to speed, and the magnetic fields keep them going round and round in a circle. Otherwise, the particles would just want to travel in a straight line. But we'll be doing some more about that with another lesson that will be completely on different types of particle accelerators. So magnetic fields, like electric fields, these are invisible, but you can make them become visible if you like. And the easiest way to do that is to use something called a bar magnet. And you might have seen these magnets. They're usually colored red at one end and blue at the other end. And normally the red end is north, what's called the north magnetic pole, and the blue end is the south magnetic pole. Now, if you just stick one of these bar magnets on a table, and that's literally how big it is. They come in other shapes as well. You can get them in what's called a horseshoe magnet shape. But we're going to look at this thing called a bar magnet. This is a permanent magnet, so it means its magnetism, if you like, is always switched on. Unlike some magnets, you can switch off their magnetism. That would be an electromagnet, where you can turn your magnet on and off using an electrical supply. But if we've got a bar magnet and we stick it on the table, and then we get something like a pepper pot or a pepper grinder, but without pepper, and it has iron filings, and iron filings are obtained if you're down in metalwork and you're cutting a piece of metal with a hacksaw. You'll get lots of little tiny particles falling off that collect on the floor, and they're called iron filings. And if you put them into a pepper pot, just a little pot with lots of holes in the top, and turn it upside down, and then sprinkle the iron filings around the bar magnet, and you give the table a tap like this, the iron filings will actually form up into a visible picture of the magnetic field. So that's one way that you can get to see the magnetic field around a magnet. Now, the Earth's got its own magnetic field, and it's got a magnetic North Pole, which actually isn't at the North Pole of the Earth. The North Pole's right in the middle of the ice in the right at the top of the world in the Arctic somewhere, and the South Pole is literally right down South Pole. And there's a permanent base at the South Pole where people actually live right next to literally a pole that sticks up out of the ground. The magnetic North Pole is somewhere in northern Canada, and it shifts around, and it's caused by molten iron in the center of the Earth rotating round and round and round, and that sets up the Earth's magnetic field. So we can get an idea of what these fields look like. You can map the fields out. If you're going to map and get a picture of the Earth's magnetic field, you'll probably need to either send somebody wandering around all over the world with a compass to see which direction the field goes in, or these days you can map the Earth's magnetic field with satellites that cover the whole of the globe in their orbit, and they will carry things called magnetometers, and the magnetometer will detect the Earth's magnetic field and will draw a map of it. And you may well have seen some pictures of the Earth's magnetic field. There's the North Pole and there's the South Pole, and the magnetic field comes out something like this. And all that shows is that if you're stood somewhere on the Earth's surface with a compass, the compass needle, and you all know what a compass is, it's a thing that you can use for navigating, like doing Duke of Edinburgh's Award. The compass needle will point towards the North Pole and will tell you where to go. We can't detect the Earth's magnetic field. We don't have a way of doing that inside us, but some animals do. I've mentioned this before. Some animals do, and they can tell which way is north and which is south. Birds, migrating birds, can tell which way to fly, even when it's dark and cloudy. They can tell which way to fly because they can sense the Earth's magnetic field, and they know the direction to go south to West Africa, where they spend the winter because it's warmer, and they come back here in our summer. So let's go back to our bar magnet, and the bar magnet has got a field around it, just like the electric fields that we were drawing before. And the way that we do these is that we always point the arrow of the field, from north to south, and the field lines go like this. And you'll need to know what the field lines look like. So you'll need to get a sketch of these. And the same rules that apply for electric fields is these field lines can't cross each other. And another little thing is that if the field lines are close together, the field is strong. They're very close together here, but they're further apart here, so the magnetic field is weaker. Of course, you want a continuous line all the way around. So that's the magnetic field around a bar magnet. And you can put in some extra lines if you want, but you'll need to get these copied down. And I'll look out a Google reference to put in the lesson so you can actually see what the iron filing pattern looks like around a bar magnet. Obviously, this one would continue round, and there'll be some other ones which are much bigger. You can actually confuse migrating birds by strapping a little magnet to their head. Apparently the magnetic sensory bit of a bird is somewhere in its brain, and if you put a magnet and tie it onto a bird's head, it won't fly in the right direction. It won't get home because the magnet sensing equipment in the bird's head and the magnet that you tie to it, they interfere. The magnet you tie to it interferes with the bird, and it can no longer find its way. You'll get the same sort of idea if you put your mobile phone close to a strong magnetic field. It's not advised if you've got loudspeakers and you've got things like USB drives. If you put them near to loudspeakers, you can actually find that the data on your phone or the data on your USB stick gets corrupted by the magnetic field that's caused by things like loudspeakers. So you need to be careful. Okay, so that's just the magnetic field pattern. Around a single bar magnet. And of course, as usual, if I'm drawing stuff on my whiteboard, you need to copy it down into your neat notes so you can remember it. Okay, so that's a single bar magnet. Now you remember when we did electric fields, we did the electric field pattern around a single point charge. This is the magnetic field around a single bar magnet. And we're going to move on with electric fields. We looked at two charges together and how the fields affected each other. We're going to do the same really here. We're going to take a couple of bar magnets. And I'm going to do south and north and north and south. And you will probably remember that two north poles will repel. It's like two like charges will repel. And if we do the other way, which is where you have south and north and south and north, these two poles are unlike, and so they will attract. And if you actually put two bar magnets like this close to each other on a desk, and you move this one closer and you push this one along closer to this one will just spin away. It physically gets repelled. And you do the same here. You push this one closer to this, and this one will suddenly jump across, and they'll end up touching each other. So I'm going to do the pattern around these two. I'm not going to do the pattern around these two here. You'll see when I do this one exactly what this one would be, because we've done it and it's very similar to the electric field pattern. Now these two are repelling. So with repelling magnets, we get fields that do this. Each magnet has its own field here, like this. But the fields from the two magnets interact with each other. So I'll just do this one. This is pretty quick to do because it's just like the other one. Remember, the arrows go from the north to the south. That's the direction of the field, from the north to the south. I suppose these ones could join up, but we end up with this sort of zone in the middle, this sort of dead zone, and it's exactly the same for two like electrical charges where there's a sort of dead zone in the middle, and there's no electric field at all because the field in the middle cancels each other out. I'm not going to do the other one with the south and the north next to each other because it's very, very similar to the unlike point charges that we did for the electric field, but you'll need to know these. Okay, so that's the field around permanent magnets. But that's just one way of producing an electric field, is to have a permanent magnet. It's called permanent because it's always on. What we want to do is have a look now at what happens if you have an electromagnet. Now, an electromagnet is just made out of a wire that has an electric current flowing through it. And this is another way of making magnets, is that magnetic fields Now, this was first discovered back in the either late 1700s or early 1800s. I can't remember exactly when, but magnetic fields can be produced by a moving electric charge. So how do you get a moving electric charge? You just take a wire and you connect up your wire up to a battery, just like that. Negative and positive, you'll get electrons flowing. So you have these moving charges flowing along the wire, and the wire becomes a magnet. If that's turned on, you've got a magnet. If you then turn it off with a switch, you've got a magnet that isn't turned on anymore. And you'll see these magnets used in things like car breaker yards, where you have an enormous, great big magnet on the end of some sort of wire connected to a crane, and the crane cable also has hanging from it a thick wire that has electric current flowing through it, and the crane driver here has a switch, and you can get an old car there, and you bring the magnet down on top of the car, and the crane driver will then turn on the current, and the car that's made of steel will stick to the electromagnet, and you can pick up the car, you can move it somewhere else, and then when you turn the current off, the car just falls off and drops down because you've turned the magnet off. Okay, so magnetic fields can be produced by a moving electric charge. Now, you can see this easily. You can't see the field, but you can see the effect quite easily if you take a compass, and normally a compass needle will point to magnetic north, and it will just sit there. There's no current flowing in the wire. The compass needle will point to the Earth's magnetic north pole. As soon as you close the switch, this compass needle will swing round and will point in a different direction. So you can take this compass and you can put it in various positions around the wire, and then you can sort of map out where the field is, because the direction of the field is indicated by which way the compass is pointing. So if for instance you took your compass and you closed the switch there, and the compass needle started pointing that way, and then it started pointing that way, and as you moved it around it started pointing in different directions, the compass needle will map out where the field goes, and then you can join up all the little compass arrows and you'll be able to see where the field is. That's not quite accurate, because I'm going to do a more accurate one in a minute. And as soon as that's when it's turned on. Let me just turn it on. Okay, and as soon as you turn it off, if you had a whole load of compasses, the compasses would all go off and point north. If magnetic north was up there somewhere, you close the switch and the compass needles all line up with the magnetic field produced, because we've got electrons moving along the cable, and all these moving electrons make their own magnetic field. Okay, now what does that look like? Well, rather than me drawing it, I've got here a little diagram that I've printed out, and you can see here that I've got a single wire, and the wire passes down through a piece of card. It's an ordinary piece of card with a hole, and you thread the wire through and you make it go round and complete an electric circuit. And all the little compasses, because there's no current flowing, all the little compass needles all point off to the north. Okay, so there's no charges moving around the circuit because the switch is open, and so there's no magnetic field produced. And the only field around all these little tiny compasses is the Earth's field, and all the compasses all point north. Now, as soon as you close the switch, all the little compass needles will line up with the magnetic field around the wire. And you'll see that if I was to join all these up, you'd just get a circle. So the magnetic field around a wire through which electric charges are moving. And what's moving? It's electrons that are moving. The magnetic field around what's called a current carrying conductor. That's a current carried in a wire, current carrying conductor, make a circular magnetic field. Okay, unlike the bar magnet, which has got a bit of a strange field, and you just sketch those down, we get a circular field. And if I put the compasses in a slightly different place, they're all out further on the piece of card, you just get another circle further apart. And if I moved all the compass needles in round there, you just get a smaller circle. So the field around a current carrying conductor is a circular one. So if I take that picture there and I have my piece of card like this, and the wire comes up from underneath and comes out the middle of the card and goes along back to my power supply like that. That's just like that. Got my power supply. Remember, electrons go from negative to positive, so I've got my electrons flowing that way. All the little arrows on the compasses, all the little needles, point round in a circle. So what I would do is I could draw the magnetic field around the wire as a series of circles, and the direction of the field is shown by the direction that the compass needles point in. So I'm putting arrows on the circles like that. Now I'm going to attach these to the lesson as a document. If you have a printer at home, you could print them out. I've done mine in color because I've got a nice color printer. You could print them out in black and white if you wanted. If you don't have a printer at all, or you've run out of ink or whatever, then don't bother printing them whatsoever. But you might like to make sure you've got this diagram here. And what we'll do is we'll just say, look, that's a compass needle, and the compass needle is pointing that way there. And you just have lots and lots of these little compasses. We've got a bag full of these in school, and what we do is we could set this up, a piece of card with a wire running through it, and you put your compasses, lots of little ones, and they're literally about the size of somewhere between the size of a 1 and 2 pence piece, and you put them all on the piece of card, and when you close the switch, they all turn round and point in the direction of the field. Okay, now a way of remembering how this works is if you take your left hand, we've got something called the left hand grip rule, and I'm going to take my pen and I'm going to grip my pen in my hand like that. Okay, and if you can see there that my thumb and my pen is the wire. Okay, and my thumb is pointing in the direction of the electrons flowing up, and my fingers are going round, and you can see the way my fingers are pointing around there shows you that the field goes round that way. If you look down on it like that, there's the current coming up the wire, and the magnetic field goes round and round like that. Okay, so I'm just holding it like that so you can see what's going on. So that's called the left-hand grip rule, and that will show you the direction of the field, if you can remember that. Left-hand grip rule shows you the current. Your thumb shows you the current, which way the current's moving, and the direction of your fingers curling around the wire show you which way the field is going. So obviously if you turned the wire upside down and you had negative at the top and positive at the bottom, the electron flow would be going down the way. So all you do is you turn your hand round the other way like that. Okay, I'll hold it up there. I'll turn it upside down, and you can see that your fingers curl round the other way, and so you change the direction of all the arrows. You take out all those arrows going that way, and you'd turn them round like that. Okay, so that's called the left-hand grip rule. So if you've got these and you fancy printing them out and sticking them in, do so. If you don't, you can't or won't, then as long as you've got the idea of this and you've got it labeled up, that's the card. And this is a small compass needle. And the compass needle points in the direction of the field. And of course, it's the magnetic field. Points in the magnetic field direction. And you could make mention of the left-hand grip rule. You could even try drawing it. My drawings are appalling, but you'd have a thumb up there, and then you'd have some fingers coming around here. I can't do this. I'm not an art teacher, so I've got my fingers curling around like that, my thumb pointing up that way. Thumb shows the electron flow, and the fingers curling round show you the direction of the field. You could have a go at drawing that if you wanted. Okay. So magnetic fields can be produced by a moving electric charge. So as soon as you turn the current on, you get a magnetic field. Known about for a couple of hundred years. And you might have made electromagnets in the past where you take a piece of wire and wrap it round and round a big nail, and you can pick up paper clips and turn off the current, the paper clips will drop off, that sort of thing. Okay. I'm just gathering my thoughts for the next bit. So just something to remember. So an electron is a small point charge, and we've done that in electric fields. So you take your electron, and it's got a field that exists around it already. So an electron is a small point charge with its own electric field. Now, if it's not moving, if this electron isn't moving, it's still got its own electric field, but it hasn't got a magnetic field. If you go back to the drawing before where I had the wire roughly like that, and I've got a switch, there are electrons already everywhere in the wire all the way around the circuit, but the electrons aren't moving. And if they're not moving, they don't produce a magnetic field. It's only when you close the switch and the electrons start moving that they produce the magnetic field. So an electron has its own electric field, which is turned on all the time. But it only produces a magnetic field when it is moving. Now it still has its electric field, but it produces a magnetic field when it's moving. So you get both fields from a moving electron, or indeed a moving proton. We don't get protons moving in electrical circuits, but you can get protons moving in the particle accelerators. You can put protons, or indeed you can put bundles of protons into your particle accelerator. Now, if you've just got a proton or a nucleus, which might have a couple of protons and a couple of neutrons, if you've just got the particle sitting still, it has a permanent electric field around it. As soon as it starts moving, though, it produces a magnetic field. Turn off the current flow, stop the proton or stop the electron in your particle accelerator, and it's still got an electric field, but its magnetic field has been switched off. So this word electromagnetism is a combination of electric, obviously, and magnetic, and the two go hand in hand. But you must have the particle moving to get the magnetic field. In addition to the electric field. Electric field's on full time. The magnetic field is switching on and off depending on whether your circuit is switched off or is switched on. Now you might ask, how does a bar magnet, sometimes people ask this, well, there's my bar magnet, and it's got a north and a south on it. Usually they're coloured. The red is north, blue is south, and you're going to say, well, okay, I don't see any electrical circuit there. I don't see the particles moving, but it's a little bit more subtle with a permanent magnet. The permanent magnet is made of millions, probably billions and billions of synchronized moving electrons. So if you were to zoom in and have a look at the particles inside a bar magnet, you'll have a nucleus of an atom sitting still, and around it would be electrons whizzing round and round and round. And in a bar magnet, the orbiting electrons all orbit in the same way. And so every tiny little atom is a tiny, tiny magnet in its own, because the electron, the charged particle, is going round and round and round. But at the same time, the particle next to it, if you were to zoom in at the particle next to it, there, you've got your nucleus. The electrons are in sync. They're moving in synchronous orbits. In other words, the electron here is moving at exactly the same way as this one's moving, and you'll have millions, billions of these atoms with all the electrons all moving at exactly the same time. And those moving charges from every little tiny, tiny magnet all add up to give you quite a strong bar magnet, even though the magnet itself isn't jumping around all over the place. And it's only in some metals like iron and nickel where the electron configuration and the way that the atoms are set out is that all the electrons are all moving in what's called a synchronous manner. That's just an aside, really, is how does a permanent magnet manage to be a magnet when it's obviously not moving around, but it's because the electrons are moving in itself. Okay, so that's this first bit of a lesson done. This is lesson 9, and I'm going to stop there, and I'm going to now record the next lesson, which is 9A, because I need a bit of a break, and you'll be able to stop and have a bit of a break as well. Remember, you can pause at any time for making the notes. You can pause the video at any time, either on your YouTube video or your Google Meet video, so that you can do the writing and you can do the diagrams. So I'm going to stop this one just for now.